In this part, we'll look at policy-based methods, first focusing on a technique called policy iteration. Policy-based methods differ from value-based methods like iteration and Q-learning. Value-based techniques first compute a value function, such as a Q function, and then extract a policy from that. In policy-based methods, we instead compute a policy directly. We'll first look at a technique called policy iteration, which is a dynamic programming technique similar to value iteration, except that it computes a policy and not a value function. It works by iterating between policy evaluation, which calculates the value of each action in the policy, and policy improvement, which improves the policy based on these calculations. Policy iteration and other policy-based methods give a lot of advantages, which we will discuss later on. After this part, you're expected to be able to do the following. Apply policy iteration to solve small-scale MDP problems manually, and program policy iteration algorithms to solve medium-scale MDP problems automatically. You should be able to discuss the strengths and weaknesses of policy iteration, and you should be able to compare and contrast policy iteration to value iteration. Let's get started. Before we start, let's just give some intuition around the difference between value-based and policy-based methods. In value-based methods, we learn a value function such as the values of these states and then extract a policy from this. In policy-based methods instead, we learn a policy directly. In policy-based methods, we first start with an arbitrary policy such as the following. Which assigns an arbitrary action to every state. We then evaluate the quality of that policy. Depending on the type of technique, the way that we evaluate that is different. We evaluate the policy by looking at each action and trying to evaluate the value that we would get if we selected that action in that state, compared to the other actions that are available. If we can find better actions, we update our policy to choose those better actions. We'll look at a model-based technique first, called policy iteration. Policy iteration uses dynamic programming in order to evaluate the policy and update it. Later on, we'll also look at model-free techniques that are similar to techniques like Q-learning and SASA that use the idea of policy gradients to update the policy. Before we get to policy iteration, let's look at the idea of policy evaluation in a model-based environment. When we do policy evaluation, we want to evaluate the value of our policy in each state. We do this using the following expression. We calculate the value of a state S given a policy pi. Note the slight difference in notation to the way we've been using value functions previously, in that we have this pi parameter here. We're trying to evaluate the value of the state S given this policy rather than the real value of state S. We evaluate it using the following. This expression might look somewhat familiar, but we haven't seen it yet. Let's have a look. So we can see this part here looks just like the Bellman equation. We're trying to measure something over the reward plus the discounted future reward. However, note the difference in terminology again here, that we're trying to look at the discounted future reward given by policy pi that we're evaluating. The second thing to notice is that unlike in a Bellman equation, where we take the best action from that state and define the value, in this case we're looking at the value provided by the actual policy we're given. So this max function is missing at the front here, and instead of looking at the best action A, we look at the action that policy pi tells us to take in state S. So this is different to the Bellman equation in that we're not trying to define the value of state S given an optimal policy, but the value of state S given a policy pi that we already have. The optimal expected reward that we could receive we'll denote as V star S. And to define that, what we want to do is we want to find the policy that maximizes the value of each state. Therefore, in policy-based methods, what we're trying to find is the policy that maximizes the value function given that policy. So here's an algorithm for policy evaluation using dynamic programming. This is a model-based algorithm because it assumes that we know the transition function and the reward function. You'll notice the similarities with value iteration. What we do is we repeatedly apply some update rule until the difference between the previous value and the old value becomes less than some predefined theta value. In each loop, all we do is look at each state and calculate the value of that state given the policy pi. We simply apply the policy evaluation definition here, and we can see here that we're evaluating the value of the policy pi in state S rather than trying to calculate the maximum value. At the end of each loop, we again calculate our delta in the same way we do in value iteration, and then assign the new policy to the old policy. So this algorithm uses this idea of dynamic programming. It uses the previous value function to calculate the new value function for this state, but it's not the same as value iteration in that we're not trying to find the best value for S, we're just simply evaluating the policy pi in each of the states that we have. We're going to use this algorithm and this definition in policy iteration in order to search for a good policy. Once we have evaluated our policy, we can improve that policy based on the value function that we get back. In policy improvement, we use the values that vpi assigns to a policy in order to improve a policy. To do that, let's briefly define a concept that should be quite familiar, but it's being used slightly differently than what we've seen before. We're going to define the Q value of a state action pair given a policy pi. This definition looks very familiar. This definition is just exactly the same as calculating the value of the state given pi, except that we're not quantifying over the policy anymore, we're quantifying over a given variable. But we use this vpi value function in order to calculate it. When we do policy improvement, we look over all the actions that are available from each state and see if we can find one that's strictly better than the one that's already in our policy. So intuitively, what we know that is if we can find an action A such that the Q value of that given the policy pi is strictly greater than the Q value that the policy already tells us, then we can improve the policy by setting pi of S to A. So if we think about these two steps, what we have is first policy evaluation that tells us the value of each state given the policy. Then we have policy improvement that says given that value function, we're going to try and look at every action that's available from each state, and if it's strictly better than the current action in the policy according to the Q values that we have from our value function, then we update our policy with that new action. So this policy improvement step is going to be a strict improvement on the policy that we already have. Now that we've defined policy evaluation and policy improvement, we can easily define policy iteration. Here in the slide we have an algorithm for policy iteration that takes an MDP and outputs a policy directly rather than a value function. The way it does this is to first create a value function that's arbitrary, as we do in value iteration, and create a policy that's arbitrary, where for every possible state we just assign some arbitrary action A. As with value iteration, the initial values of these don't affect the final result. What we do in policy iteration is we repeat the following steps until our policy stops changing. First, we compute the value function v of pi s for all states using policy evaluation. This gives us the value of each state for the policy we have. Initially, that policy is arbitrary, so we have the value of all the states for some arbitrary policy. Then, for each state S, we simply iterate over all the possible actions that are available from that state until we find the action with the best Q value according to our Q value based on that policy. And we assign this. So all this algorithm does is simply iterate between policy evaluation, judging how good the policy is, and policy improvement, updating the policy based on the policy evaluation we just had. It will do this until the policy pi no longer changes. That is, none of the actions in the policy have changed from the start of the iteration to the end of the iteration. At that point, we've reached convergence. Doing another iteration of the loop couldn't possibly change the values because the same value function will be calculated and the same update will be done. So we can see here this idea of policy iteration using dynamic programming is a combination of policy evaluation and policy improvement. What's interesting about this is that policy iteration will finish with an optimal policy after a finite number of iterations, because the number of policies is finite and we strictly improve the policy on each iteration. The number of iterations of this outer loop in policy iteration is strictly bound by the number of actions that we have in our MDP to the power of the number of states. That's the worst case complexity. Quite often we find in policy iteration we converge quicker than that. So unlike in value iteration, which theoretically requires an infinite number of iterations, policy iteration is bound by this expression here. However, each iteration has quite a high cost. Doing the policy evaluation for every state has a worst case cost of the number of states cubed, while the update has a cost of the number of states squared times the number of actions in order to do the update. This is a worse inner loop complexity than the value iteration, but empirical evidence suggests that the most efficient choice, policy iteration or value iteration, is actually dependent on the particular MDP model that we're trying to solve, and that surprisingly few iterations are often required for policy iteration to converge. Similar to value iteration then, this algorithm will scale quite well on medium scale problems, but will suffer in massive state spaces. So now let's look at an example of policy iteration using Gridworld. We're going to look at this state here, state 2.2, and we're going to assume that initially our policy pi for state 2.2 is action up, telling us to go up in that state. We'll assume that this is the first iteration, and we also will assume that v of state 3.2, which is our goal state here, is going to be 1, which it will be after the first iteration. We know this because, as you can remember from the notes, we get a reward for transitioning out of our goal state into some dummy terminal state t of 1, therefore our value will be 1 after one iteration. So let's look at the update of our value at state 3.2. What we have to do is calculate this state 2.2. It's going to be equal to all the possible states that we will reach if we choose up, which we will know will be, with 0.8 chance, it will bounce back to 0.2 off the wall, with 0.1 go left, with 0.1 go right. So the value is going to be first the probability of going up successfully, which will bounce back into state 2.2, which is 0.8, times by the reward we get for that, which is 0, plus gamma 0.9 times the value of the state we come back to, which is state 2.2. And the value of state 2.2 for now is going to be 0. So that's the one outcome. The second outcome then is 0.1 if we go left. If we go left, we'll successfully go left, we'll bounce left accidentally, we'll get no reward, and a gamma of 0.9, and the value of our state is going to be 0. And 0.1, if we go right, we'll get no reward, 0.9, but the value of our state here, as we've established already, is 1. Therefore, that will be 1. And therefore, the value of this expression is just 0.9 times 1 times 0.1, so 0.09. So that gives us the value of the state 2.2 if we followed the policy where pi tells us to go up from state 2.2. And we'd have to repeat that for all states in order to get the value before we do the policy improvement. When it comes time to do the policy improvement, we can calculate Q of pi for 2.2. We will notice that if we go right, we get a better value than if we go up. We'll notice this because if we go right, we have a 0.8 chance of going right. We'll get a reward of 0. 0.9 times the value, which is 1, plus 0.1 chance that we'll go to the left, in which case we'll bounce back into state 2.2, which we've already calculated gives us 0, plus similarly would go down, would be 0.1, 0. This expression summed is 0.72. So now what we can see is that the value of going right from state 2.2 is 0.72, which is strictly better than the value of going up from state 2.2, which is 0.09. So our final step then would be to update the policy from state 2.2 would then become go right. So that would be one step through the policy iteration algorithm, where we iterate over doing policy evaluation for each state, then doing policy improvement for each state. In this case, we get a strictly better policy, and we would see that we would get better policies in other states as we go through a few iterations. Now let's look at an example of policy iteration in action over several iterations. We see here on the screen the example of Gridworld at iteration 0. I've initialized the policy arbitrarily to the action go left for every possible state. I could have done it as a random action, but I chose left. We can see here that after one step, we do policy evaluation and policy improvement, and our policy changes entirely. Every state now goes up. That is probably an improved policy on before, but it's still not a great policy. When we step through to iteration 2, we can see a much more improved policy here. We can see that our actions are starting to gravitate towards the goal, but some of them aren't quite there yet. We're going right in this state here, which is not optimal. But then we change in iteration number 3 here, and we end up with actually what is the optimal policy. As we can see, if we play it through, it's already converged. It doesn't change at all. And we know at that step between 3 and 4, when we apply policy improvement, when the policy doesn't change, we know that we can successfully terminate the algorithm there. This is quite a small example here, but if you look at the notes into a larger example where we have a grid of, I think, 20 by 15, you can see that the convergence takes a lot more than 3 iterations. I believe it's something like 19 iterations. So the convergence, the number of iterations we have to do, is dependent on the state space and the action space as well. In this part, we discussed policy iteration, which is a policy-based method for solving MDPs. Policy-based methods calculate a policy directly, which is unlike value-based methods, which calculate a value function or a Q function and extract a policy from that. Policy iteration is a dynamic programming technique for calculating a policy directly in model-based settings. It iterates between two steps, policy evaluation and policy improvement, and it produces an optimal policy in a finite number of steps. Similar to value iteration, this works well for medium-scale problems, but as the state space grows, it doesn't scale so well. Next, we'll be looking at model-free policy-based techniques, so stay tuned.